I talk about feature learning, which is a key topic within machine learning. Feature learning methods are very important tools within machine learning. And in order to place this lecture in the whole course, I first ask you the question, what are three components of machine learning? Yes, so I have here an answer on the chat. So the three components are data, hypothesis space, and an error measure or a loss function. Today we will focus on the component data. In particular, we will hear about methods that allow to automatically learn good features of a data point. As you remember, a data point is characterized by features, which are quantities which we can in principle measure or determine or compute easily or in an automated fashion. And they are not there, but there's also another type of property or aspect of data points. Does anyone remember which other type of properties a data point could have? Labels, yes. So these are the higher level facts or the quantities of interest. But today we focus on these properties which we can measure easily. And typically we have a lot of these properties. Nowadays, and I will show them a few examples, application examples, where we see that we can, in principle, compute a lot of features for individual data points. We typically have too many features, so that we are overwhelmed by the amount of features, but we need to pick the most relevant one. And I will tell you why this is important. So we will talk about the challenges that come with long raw feature vectors when we have a lot of features for individual data points. Then I will explain the basic idea of feature learning, which is to extract the few most relevant features. Then we will see how we can use feature learning to visualize data and also to protect privacy. A key branch of machine learning nowadays deals with privacy preserving machine learning. We want to extract all the information from data that we need for a certain prediction, but not too much. And in particular, we want to protect privacy of persons. Then I will focus on one particular feature learning method, which is called principal component analysis. It turns out that principal component analysis is in some sense an optimal feature learning method when we constrain the learning method to linear maps. Beside principal component analysis, there are also other feature learning methods, and I want to briefly introduce one such method, which is based on random projections. Okay, so this is the agenda for this lecture. Are there any questions at this point? Okay, so let's consider a typical conversation as it can happen in the beginning of a movie night or an evening, and you want to watch a movie with your partner. And then there's always this big question in the beginning, what movie should we watch? And then partner B proposes a certain movie, which I like very much, and the other partner is not the same opinion. So here we would like to somehow explore movies. So we can model this as a machine learning problem by identifying movies as data points. So we can say a data point is some movie. For example, this movie here, which is called The Campaign with Will Ferrell and Zach Galifianakis. And what features could this data point have? Does any one of you have an idea what we could use as features of this data point? The genre, yes. The actors, yes. Which actors? The director, the length, yeah. But in the end, in the very end, how do we store a movie? How do we access a movie on the lowest level of information or data? Well, there might be, yes, as bits data as we use it in this course is in the end nothing but a pile of bits. And also a movie, for example, it's stored as an MP4 file, is a bunch of bits and a lot of bits. So typically gigabytes if it's a high definition movie of 2 hours duration. And in principle, we can use all those bits as features, or we can group the bits into bytes, or we can group the bytes into several bytes which represent a floating point number or an integer. And we can then stack all these integers that we get into a feature vector with millions of entries. So we have extremely long feature vectors. Yeah, and typically we not only have one movie, but you have now these streaming services which have a lot of movies to offer. So you have now this challenge of finding a good movie. So often having too much choice makes the life not easier, but quite opposite, more challenging, because then you're always forced to find to look for the good choice, or what is the good choice. So what we would like to do is we would like to somehow navigate the movie space. So we would like to have a 2D representation where points represent movies. So this here is one movie, this here is another movie, another movie, another movie, and we then could explore. So, well, I like this movie very much, so this is the campaign. It is here. And then we can say, okay, what is nearby? So this is another movie. Maybe the other partner also likes this movie. And since it's nearby my original proposal, it might also be convenient for me or interesting to me. So we would like to navigate this movie domain. Does any one of you know about such a visualization tool for movies, by the way? Yeah, I'm not aware of such a tool, so this could be one topic for a student project or a business idea maybe. If you really work out this nicely, you could develop an app and make money with that app. Okay. Oh, yeah, so there's one comment. Netflix does that. Yeah, it does it. I guess it's implicitly done in the recommendation system or a recommendation engine of search or of streaming services, movie streaming or movie or film streaming services. But I don't know. I didn't see it that Netflix or other streaming services offer such a visualization tool where I can navigate the movies on a 2D plane. And this is exactly what we can do with feature learning. As soon as I have a method that takes one data point and somehow extracts two most relevant features, so which I call x1 and x2, whatever that is. It might be, for example, the duration. X1 might be the duration, and x2 might be the average greenness of all movie frames or scenes. But in general, this will be highly abstract quantities, so it's not easy to interpret them by simple characteristics. So, but for feature learning methods, they don't care. They just learn two features, give them a certain criterion, and we can then use these two features to represent high-dimensional data points as a scatter plot. And it's just one example, a movie. There are other examples like whenever you deal with humans, so one data point represents a person, we typically have way too many features or extremely wealth of features a large number of features for each individual person. We have basically all health records if they're accessible, which could include the genetic fingerprint, any medical diagnosis if you had run a EEG recording of your brain or any other part of your body. So all these recordings are features, all the credit card transactions you did, any social media posts you have done, or all your media collections that you have, the movie or watch lists on streaming platforms, or also your travel profile over the last 20 years. So this tons of features is extremely high. It belongs to an extremely high dimensional space. So if we stack all these quantities into a vector, we get vectors of length millions, billions. But feature learning allows us to reduce this, to compress the information in this many features, for example, into two numbers. And this, once we have these two numbers, we can use them as coordinates in a scatter plot. And we can then represent persons on a 2D plane and get some idea how the persons are related, which persons are closer to each other than others. So visualization is one key application domain for feature learning methods. So whenever you use feature learning methods, just use two features or learn two features, and you can use these two features to represent the data points in a scatter plot. Okay. Besides visualization, feature learning is also important in terms of statistical properties of machine learning methods. It turns out already for the simplest case of linear regression, whenever you have more features, so n is the number of features, and whenever the number of features is larger than the number m of labeled data points that you have, you will overfit. You will almost for sure overfit unless you do some regularization techniques or some more advanced techniques. But whenever you use plain vanilla or the basic form of linear regression, and you use more features than you have labeled data points, you will overfit. And overfitting means that you only do well on the training data set, but the validation error or the error on new data points will be large. And so this fact you get out of simple linear algebra. So the derivation of this result of this threshold is beyond the scope of this course, but you got a taste of it already in round 2 and round 4 coding assignments, where you saw that the validation error goes up if you use more and more features. And the turning point or the critical point is exactly given by the number of labeled data points. So whenever you use plain linear regression, you need to have way more or a good number of multiple times number of features. You need to have labeled data points. So, and when you have billions of features, or for an image that you take with your smartphone camera, which has megapixels, so if you stack the pixels into a vector, you get millions of entries, or a feature vector of length millions. You need to have millions of labeled data points for anything you want to do with linear regression on that snapshot. So often you don't have that many labeled data points. So what you can do is you can work on this n here. So you can reduce the number of features. And you can do that using feature learning methods. Okay, so here's the basic idea of feature learning methods. And this basic idea is quite simple and intuitive. So what we would like to do is we want to find a map that takes a raw feature vector, for example, all the pixels of all the frames of a high definition video, which are some billions of numbers. So this is the raw feature vector. And we apply some map which we can tune. So a map which includes parameters which we can change to get a shorter feature vector x. And we tune, or we choose this map or the tuning parameters such that we can find another tuning of a map, or another map that we can tune such that the reconstructed feature vector has a small deviation, or deviates only little from the original raw feature vector. So this might sound a bit abstract, but let's look at particular examples. So do you know examples of a tunable mapping that reads in a feature vector, a long vector, and outputs another vector. Does anybody of you know such maps that can do that? A map in the sense of a function, a mathematical function that takes some vector as input and outputs another vector. Yeah, the mean, for example, just computing the mean, this how long is the short feature vector then? If we compute the mean of all the entries of C, so the short feature vector would then be length 1. Yeah, if we compute the mean, then it's 1. Can we do a map that outputs more than one number? Rolling average, yes, but these are all special cases of a matrix multiplication. So the special case of linear feature learning methods is given by using linear maps for the compression and reconstruction. So a matrix can be used to represent a map that reads in a feature vector, a raw feature vector C, and we apply the map by multiplying the matrix W with C and get another vector X. And if we choose this matrix W to be wide, to have more columns than rows, then it does exactly what we want. It reads in a long raw feature vector, and it outputs a short new feature vector. So a matrix is a tunable map. A matrix represents a tunable linear map. And we can use another matrix for this other tunable map for reconstruction. So this is this matrix R. And then linear feature learning amounts to choosing W. So this are something like weights that we can change. So this matrix, or the entries of the matrix W and the entries of the matrix R, we can tune, we can change, like the weights in a artificial neural network, or like the weights in a linear map. Okay, and we choose them such that this reconstruction error is as small as possible. But this is only one example. So a multitude of feature learning methods arise from using different types of maps. So do you know another type of map that we can tune besides linear maps? What other function classes did we consider in this course? Or sets of different functions? Well, we consider different hypothesis spaces. A hypothesis space is exactly a set of functions. So what hypothesis spaces beside linear spaces did we look at in this course? Well, another example would be decision trees. So we could use here decision trees to map from raw feature vector to a short feature vector, or polynomials, or we could use an artificial neural network. In the end, an artificial neural network is nothing but a map, a rule that defines how we take an input vector and produce an output vector. And this rule can be tuned or adapted or changed by weights, by choosing weights. So these weights, each edge is associated with a weight, which we can change, which we learn using some training data. Yes. So if we use artificial neural networks for this compression and reconstruction maps, then the resulting feature learning method is called sometimes an autoencoder. Okay. But so far, we only talked about unsupervised feature learning. So we didn't consider any labels yet. So we just wanted to learn features that allow to reconstruct the original raw feature vector. So this is nothing but compression, typically lossy compression, because we will not be able to make the reconstruction error exactly zero. We typically accept or tolerate some reconstruction error because we want to have a compact and very efficient representation of efficient number of features for data points. But if we have labels, if the data is such that we can define labels for data points, then we should use other criterions instead of the reconstruction error for choosing this compression map. In particular, we should choose this compression map such that we could find another map which can be tuned to reconstruct or to predict the label. And then again, we obtain different feature learning methods by using different types of tunable maps, either linear maps or artificial neural networks or decision trees or any other class of functions. Yeah. And this choice or this tuning of the map needs to balance between two conflicting criterions. The first criterion is the compression factor or the compression rate. So we want to compress as much as possible to get a short feature vector. For example, for visualization, we only want to have 2 feature entries here. But there's a limit to how much we can compress the raw feature, because this raw feature contains some information about the label which we want to predict, and we need to keep the relevant parts of the information. Otherwise, we will lose relevant information, and we cannot in any way predict the label from this new feature vector X. Okay. So any questions up to this point? Can you hear me? Is there a problem with the audio? Okay, so it's just that there are no questions. Very good. Okay. Yeah. So besides allowing to visualize data as scatter plots and also to help avoiding overfitting, which appears to happen or is likely to happen if we use too many features, another use of feature learning methods is to ensure privacy preserving machine learning. So here we use a compression map W to serve 2 purposes. The first purpose is to be able to predict the label or the quantity of interest. But there's another purpose, that is, we want to hide away any private information which is contained in the raw feature vector. So this vector X, this new feature vector X, should only contain anonymous data in some sense. So we would like to choose the tunable map such that X, the resulting compressed feature vector, does not contain any relevant information about a private variable s. So this s is something like another label. So each data point is assigned two label values or quantities. One is y and one is s. Y is what we would like to predict using our machine learning method, and s is the private information that we do not want to touch. So I have here an example for food recommendation. So what we would like to do here is we want to find out for a certain person if the person prefers apple or pizza. So the quantity of interest y of a person is either pizza or apple. But then there's another variable or quantity for each person, which is the gender. So either male or female. And we would like to ensure that this information about the gender is not used at all in our machine learning system. So we want to get rid of any gender-specific information as quickly as possible, right from the first processing stage. However, we still want to keep the relevant information that allows us to predict if a person prefers apple or pizza. And this is what we can do using feature learning methods by using different learning criteria. So I will not go more into detail here, just want to mention that these feature learning methods are also useful for privacy preserving machine learning. And this becomes more and more relevant in applications. Okay. So let's now focus on linear feature learning. As I already discussed, in linear feature learning, we use only linear maps. We use a linear map for the compression. So we take the long feature vector C to a short feature vector X by multiplying with a matrix W. And this matrix W represents the compression map. And we can tune this compression map because we can change the entries of this matrix W. So here we have the first row of the matrix, W1N. And here we have the first column of the matrix, WD1. Here we have the final entry, DN. Sorry. So, and then in linear feature learning, we want to find the matrix W and an accompanying matrix R, a reconstruction map R, such that the reconstruction error between the original raw feature vector C and the reconstructed feature vector C hat is as small as possible. And it turns out that the optimal choice for the compression matrix can be found in closed form using the eigenvalue decomposition of a certain covariance matrix. So just to calm you down, you do not need to understand the details of eigenvalue decompositions for this course. So in this course, we will use ready-made Python functions to compute this principal component analysis. But I just, for the sake of exposition, I want to also discuss this briefly, how we obtain the optimal compression matrix W and corresponding reconstruction matrix R. And this, in particular, this optimal compression matrix is obtained by the eigenvectors of this sample covariance matrix, which correspond to the d largest eigenvalues of this sample covariance matrix. So the sample covariance matrix represents the similarities between the different entries of the raw feature vector. And you can compute it using a sample average of this matrix product. Okay. So after you compute this sample covariance matrix, you compute the eigenvalue decomposition of this sample covariance matrix, which is guaranteed to exist because this matrix is a positive semi-definite matrix. And then you can conveniently read off the row, or the rows of the optimal compression matrix are given by the first few eigenvectors of the sample covariance matrix. So typically you do not take all these eigenvectors, but only the first d ones. And this d, the number of, or the length of the smaller new feature vector, is typically much smaller than n. N is the length of the raw feature vector. These are the billions of features of a movie, for example. Okay, so in the end, mathematically, principal component analysis is more or less equivalent to an eigenvalue decomposition of a positive semi-definite matrix, in particular of the sample covariance matrix. Yeah, but as I already assured you, you do not have to compute eigenvalue decompositions by yourself, but there are nice Python functions for this, as you will see in the coding assignments in the Python notebook for round 6. Just to give you an idea about the meaning or the role of this eigenvectors U. So if you have a data set with raw feature vector C, which looks like this, so what you get in PCA, the rows of the optimal compression matrix. So here, this is the first row. And then we have the second row. So these rows turn out to be the directions in which the data points change the most. So this is the first direction in which the data points spread out the most, and then the second direction in which the data points spread out the most. If we remove or if we ignore the variation in the first direction. Okay. Yeah. So, although it seems quite easy and straightforward to implement PCA, it is typically not, because in order to compute this eigenvalue decomposition this year, we need to invest a lot of computational power, and this becomes significant for long feature vectors, which is often the case in big data applications where the raw feature vectors have billions of entries, and then computing eigenvalue decomposition of the sample covariance matrix, which is of dimension billions times billions, is highly non-trivial and might take a lot of computational resources. Okay, and therefore I want to briefly also introduce another method for dimensionality reduction, which doesn't need any principal component analysis at all, and which is based on random projections. But before that, I would like to briefly go over a few variations of PCA. So the first variation is robust PCA, which uses a different measure for the reconstruction error. Yeah, I didn't make it explicit, but here we always need to define some measure. So which component is this when we need to define how we measure errors? What component of machine learning is this? How to measure errors? Which function do we use to measure errors? Loss function, yes. What loss functions do you know? Which loss functions did we hear about? Squared error loss, yes. So we could use here the squared error loss, or if it's a vector, so since it's a vector, we use the squared Euclidean norm, which is the generalization of the squared error loss to more than one difference, but a whole vector of differences. So we can use the squared error norm here. And so this PCA is based on minimizing the squared error norm. But if we use another norm, we obtain linear feature learning methods different from PCA. And we will look at this now, which is called robust PCA. So robust PCA is beneficial when you know that you have some outliers. And it turns out you can make PCA robust by changing the loss function. So do you remember we had a similar strategy already in regression? We changed the loss function to become more robust to outliers. Which loss function did we use then? Hoover loss, or the absolute error loss. Exactly. So robust PCA is based on using the Hoover loss or absolute error loss instead of the squared error loss. Another special case or variation of PCA is probabilistic PCA, which uses a probabilistic model for the data points. So far, we didn't use any probabilistic modeling, but there's nothing to prevent us from interpreting the data points that we observe, for example, the movies that we have in our database, as realizations of a random vector. And in probabilistic PCA, we assume that these realizations are drawn from a multivariate normal or Gaussian distribution. And probabilistic PCA then amounts to estimating or fitting a Gaussian distribution to the observed data points. Okay. Yeah, then there's also another variation which I will not talk more in detail, which is called Sparse PCA. And here, in Sparse PCA, we modify original PCA such that each new feature depends only on few raw features. Because in standard PCA, or plain vanilla PCA here, in principle, this this vector X contains the new features, the compressed features. Let's say we use only 2 in order to visualize the data in a scatter plot. So we use only 2 new features. And per se, or in principle, this new feature X1 could depend on all the original raw features. And also X2 could depend potentially on all original raw features, since this matrix W could contain everywhere non-zeros. However, in sparse PCA, we force these rows of the matrix, of the compression matrix, to have only few non-zeros, which means that each new feature depends only on a small number of raw features. And this is sometimes beneficial because we can interpret then these new features better, since this new feature then corresponds only to a certain group of raw features, and this group might have some meaning. Okay, so these are the variations of PCA. Regarding the usage of PCA, I guess you have to combine PCA with linear regression or classification in the coding assignment, and the idea is, instead of using the raw features of a data point, use the compressed features. So first we do a feature learning. We apply feature learning, for example, PCA, to learn a compression matrix W. And then we apply the compression matrix W to all the raw feature vectors of the training data points and get this short feature vectors X. And we then continue as in round 2 or round 3. So after learning the compressed features, everything is the same as in the previous rounds. And we throw away the original raw features after we have learned the new short features. Okay, but the important thing here is this might sometimes not work well, because PCA, the plain vanilla PCA or the standard form of PCA, ignores the label information. And I want to illustrate this with a very exaggerated example or pathological example where we have a binary classification task. So we have two label values, a triangle and a circle. So each data point either has label triangle or circle, and we would like to find a a classifier that tells us if a data point is a triangle or a circle, based on the features, on the raw features C1 and C2. However, we do not want to work directly with the raw features because 2 features are too much. So we want to use feature learning to reduce these 2 features to 1 feature. So we use PCA using 1 compressed feature. So what direction will PCA use, or what will be the new features look like? Well, according to this basic principle of PCA, it will look at the direction of the largest variation, the largest variability of the data points, and ignoring the labels. So it doesn't look at the label. PCA is blind to the label. It just looks at the location of the data points, and these locations tell PCA, well, the variability is maximum in this direction. So it then projects all these data points onto this direction, and it replaces the original data points with these new features, which are points on this direction. And as you can see, data points with different labels almost lie on top of each other in this new feature space, or using the new features, which is clearly not good, because I want to distinguish between triangle and circle. But if I use PCA and use the new feature for each data point, so I project these original data points onto this line, they almost lie on top of each other, which is very bad. What I would like to do instead, I would like to use this direction here, because in this direction, if I project the data points on this direction, all the triangles end up here on this point, and all the circles end up here at this point. So there's a clear separation in this new feature space. But PCA would not pick this. Instead, PCA would pick this bad direction because it ignores the labels. So you should not always or naively use PCA for pre-processing because it ignores the label data. You should use a different way to train the compression matrix, which somehow takes into account here the prediction of the label. Okay, so the final part of the lecture discusses an alternative to PCA. As I explained, computing this compression matrix W using PCA might be computationally infeasible when you have long raw feature vectors of the size of billions, because computing the PCA of a billion times billion matrix is highly non-trivial and might require cloud computing, and these resources might not be available for a given application, which has to run, for example, the application has to be implemented on a smartphone app. And an alternative to PCA is to do random projections. So what we do here is we choose the matrix W by filling it with random numbers. So we choose each entry of the matrix W by random draws from some distribution, for example, Gaussian random variable random numbers, or Bernoulli, -1, +1. And then we use this compression matrix to get new features or short feature vectors. So the important point here is that there is no learning, no tuning, or no eigenvalue decomposition involved here. If you can easily generate random numbers, then you have no problem, computational complexity problem here. You just generate the matrix W and apply it as often as you like. And it turns out, in many settings, this works extremely well, almost as good as doing PCA, this computationally expensive optimum linear feature learning. And this using random projections is also known as compressed sensing, which is one of the hot fields, I would say, the last 10 to 15 years in signal processing or machine learning. However, it is not extremely well understood when compressed sensing is, or when these random projections are guaranteed to perform close to optimal feature learning. But in some simple settings, like linear regression settings, it can be shown theoretically that these random projections come very close to the performance of PCA. But for random projections, we don't need any computationally expensive matrix operations, which is the big advantage of random projections. Okay, so to sum up today, I have tried to make clear to you that we need to avoid long raw feature vectors. So it's typically not a good idea to just take whatever you can measure, stack it into a long feature vector, which is of size billions or of length billions, and then apply some machine learning method like linear regression or apply artificial neural networks. It often makes sense to try to learn a few relevant features. For example, learning only 2 features to obtain a scatter plot and get some intuition or some understanding of the structure of the data set. Then we discussed in some depth the optimal linear feature learning method, which is given by PCA. PCA amounts to eigenvalue decomposition of the sample covariance matrix, which is computationally expensive when you have very long raw feature vectors. And then you might consider random projections as a computationally cheap alternative, which, however, can be quite effective, and you will not lose much performance compared to this optimal PCA feature learning. Okay,